This is benzene. It's a flammable aromatic hydrocarbon that can be found as a building block in a wide variety of materials, including plant-derived natural products, mammalian neurotransmitters, and synthetic substances such as plastics, dyes, and pharmaceuticals. So why is it so prevalent in nature? Well, like all organic molecules, its structure defines its function, and benzene has a trick up its sleeve that has captivated chemists and tail-eating snakes for centuries. Its very high stability. Hi, I'm Sam, and I'll be presenting on avoiding cancer while determining the resonance stabilization energy of benzene. To better understand benzene's resonance stabilization energy, let's compare the structures of cyclohexene, cyclohexo-1,3-diene, and benzene. Each cyclic molecule has an extra conjugated double bond. So let's see what happens when we hydrogenate each molecule with H2 on a palladium catalyst. We'd get cyclohexane each time. We'd expect the energy released to increase by the same amount, 1 double bond's worth. Hot damn! What happened to benzene? Its heat of hydrogenation is even lower than the one for cyclohexo-1,3-diene. Well, it may have released much less energy than we expected because of its resonance stabilization energy. The pi electrons of benzene are delocalized, hypothetically giving it much more stability than otherwise expected. In fact, if we did this experiment, we'd notice just how hard it is to hydrogenate benzene by the harsh conditions required, 180 degrees Celsius and 30 atmospheres of hydrogen. So why do we care that it's especially hard to hydrogenate benzene? Well, understanding benzene's resonance stabilization energy can help us, as chemists, to answer a lot of questions about benzene's unique reactivity and physical properties. Why, for example, does HBr undergo addition to cyclohexene, but the same reaction doesn't happen to benzene? In fact, if we want to brominate benzene, we need to use much harsher Lewis acid catalyzed conditions. Furthermore, why does benzene have such a high melting point as compared to other hydrocarbons of similar chain length? And how do we plan syntheses that involve benzene and benzene derivatives? All of these questions can be answered with an understanding of aromaticity and by determining the resonance stabilization energy. Let's do so and set forth a clear hypothesis. The observations we've noted so far would only be true if benzene had a non-zero resonance stabilization energy. So how do we figure out this energy for benzene? One way is to use molecular modeling software such as Cygress to run the energetic calculations for us. But if we want to determine it experimentally, because we can't use the forbidden snack itself, we have to approach this question in a roundabout way using Hess's law. Consider the theoretical isodesmic reaction in which benzene reacts with cyclohexane to form CDDT. In the gas phase, the heat of combustion of CDDT should equal the sum of the heats of combustion of benzene and cyclohexane. But reality check 1. If our hypothesis is correct, then benzene has a stabilization energy. So we account for that in the equation whose net heat of combustion equals the energy for benzene. This looks good until reality check 2. The reagents we can use are liquids at room temperature, and we must consider their heats of vaporization. Then, when we consider all the complications of running this experiment under laboratory conditions, we're left with this Hess's law cycle. Values A, B, C, and F either involve benzene or vaporizing hydrocarbons, so these values must be determined from the literature. But values D and E are heats of combustion that can be calculated from calorimetry experiments. When we sum all these values together, many of the components cancel, leaving the net reaction of benzene reacting with cyclohexane to yield CDDT. And, as was mentioned before, the net energy of this reaction is the resonance stabilization energy of benzene. So how then do we set up an experiment that allows us to measure the heats of combustion of cyclohexane and CDDT? Well, herein lies bomb calorimetry, where a sample is ignited under constant volume conditions. The principle is that a flammable material detonated in the presence of excess oxygen will fully break down to water and CO2, releasing all the energy in its chemical bonds as heat. If this heat is contained and measured, the energy present in the molecule can be determined. So first, the compound of interest is loaded into a sample basket with a fuse passing between the two holding arms. Then the bomb is filled with 30 atmospheres of oxygen. Next, the bomb is placed in a calorimeter bucket and 2 liters of water are added. The lid of the bucket is secured, the stirring is turned on, and a thermocouple probe is attached to measure the temperature. The bomb is then detonated. Finally, the data is collected as a function of water temperature versus time. Now that we have an experimental plan in mind, we can begin with the arduous task of solving for each term in the Hess's law equation. 4 of the terms can be determined from the literature, and values A, B, and C are given below. Value F, the heat of vaporization of CDDT, can be determined from data collected by Raw et al. Using the Clausius-Clapeyron equation. With 1 over T on the abscissa and natural log of P on the ordinate, the slope of this plot is the heat of vaporization divided by the universal gas constant, such that the heat of vaporization can be determined as 47.672 kilojoules per mole for CDDT. The remaining two values, which are the heat of combustion of CDDT and cyclohexane, can be determined experimentally. This figure shows the data collected during the first run of the calorimetry experiment for CDDT, plotted as a function of temperature versus time. You'll notice it's labeled at 5 different key points: I, A, B, C, and F. Point I is the initial temperature of the water bath, and point A is the temperature at the moment of ignition. In this graph, it's the same temperature as point I, but in other runs it varies slightly. Point B is the temperature when the water is at 60% of the max temp. Finally, point C is the max temp itself, and point F is 90 seconds after. But the good insulation and water's high heat capacity means this value is only slightly lower than point C. For each experiment, the difference in temperature must be determined. In principle, the change in temperature is the max temp minus the initial temperature. In the graph, that will be point C minus point I. But the temperature is not stable at the very beginning and the very end. Therefore, we have to do some baseline correction, accomplished with this equation. Plugging in the appropriate values for this experiment, the change in temperature is given as 4.462 plus or minus 2.1 times 10 to the negative third degrees Celsius. The same process is done for each of the trials to yield the values below. Once we have the change in temperature, we can determine the total heat transferred, Q total, via the equation Q total equals negative C bomb times delta T. The heat capacity of the system was determined using a benzoic acid standard, and an example calculation and the values of Q total for each run are provided in Table 2. But it wasn't only the sample that produced heat in the bomb. We also added a fuse to serve as a source of ignition, and for the cyclohexane we needed to use a gelatin capsule. Taking the energy released by these components out of the Q total yields the Q sample, the value of which are given in Table 3 shown here. Now, finally, we can solve for the heat of combustion for the two liquids. The determined Q sample is equal to the change in internal energy of the system, delta U, and we can use this to solve for the heat of combustion. The only remaining part of the equation is to figure out delta N gas, the change in the number of moles of gas during the reaction. For CDDT, we see that we use 33 over 2 moles of oxygen during the combustion process and create 12 moles of CO2 as a result. The net change is negative 4.5 moles of gas. We can scale this value by accounting for the number of moles of reactant used. Then calculating the heat of combustion tells us that 45.36 kilojoules of energy, with some air, were released when 6.22 times 10 to the negative third moles of CDDT were reacted. Dividing the moles of CDDT yields its heat of combustion per mole, calculated as negative 7,292.6 kilojoules per mole with some air. The same is done for each trial, and the average of the results are taken. We've done it! The table below shows the heat of combustion of each material, and these are values D and E in the Hess's law table. All we have to do now is sum together the literature values and the determined enthalpies to give us the resonance energy of benzene. The value is approximately 139.37 kilojoules per mole, or 33.31 kilocalories per mole. The value we determined experimentally can be supplemented with an additional approach to determining benzene's resonance stabilization energy. The molecular modeling software SciGrass, for example, can determine the heat of formation for any chemical, assuming, of course, that it's drawn correctly. Recall that in the gas phase, the enthalpy of the hypothetical reaction between benzene and cyclohexane to form CDDT is benzene's resonance stabilization energy. SciGrass can determine the heat of formation for each reagent, and their calculated values are provided here. From these, it's straightforward to determine the stabilization energy, approximately 148.7 kilojoules per mole, or 35.54 kilocalories per mole. When we compare the values from both methods, the first notable observation is that the two are very similar. They're within 3 kilocal per mole of each other, or within about 7%. This gives us confidence in both methods. So what are some reasons for the difference? Well, first, there was some variance in the change in temperature for cyclohexane, even after accounting for the difference in moles. More runs should give a more confident result in a smaller error. Additionally, the determined heat capacity of the calorimeter was calculated for 2 liters of water, such that small differences in measured volume could significantly impact the final enthalpy. For the cyclohexane runs, too much water was added to the bomb during the experiment, leaving the capsule remnants soaked and impossible to weigh, so this was not accounted for. Finally, even though it was encapsulated, there's always the risk of evaporation of cyclohexane. But I'm hesitant to say that the Seigres method is more accurate, since multiple Seigres attempts also yielded different results. The value given is the average of 3 attempts. Nevertheless, the values are very similar. So how can we contextualize the extra 34 kilocalories per mole that benzene has? Implications are felt in organic reactions like electrophilic aromatic substitution that require harsh conditions, in enzyme structures that are adapted for handling uniquely stable benzene and benzene derivatives, and physical chemistry principles that define aromaticity and delocalization. Fundamentally, the stabilization energy of benzene quantifies an otherwise abstract chemical principle, which can be explained with this graphic. Linear conjugated systems, like the two on the left, leave carbocations and carbanions when they resonate, making the equilibrium unfavorable. Cyclic compounds like COT are anti-aromatic, disobeying Huckel's rule and making their delocalization unfavorable as well. But benzene is ideal. Its small size gives it the greatest energy savings per carbon. Since the method we used is just one example of an isodesmic reaction, are there others that we can use instead? Absolutely. Consider this Hess's law cycle that uses the reaction of benzene with ethene to yield COT. We can use this method by deciding to neglect any resonance energy in COT, even though the molecule does have conjugated double bonds. But that doesn't mean none exists, and the method will probably yield less accurate results than the one used in my methodology. Or we can try our hand at the hydrogenation experiment described at the beginning. In future experiments, it will be interesting to consider the resonance energy of activated and deactivated benzene derivatives like aniline and nitrobenzene, as well as larger aromatics such as naphthalene. The resonance energy per carbon can be calculated as well.
Overall, it seems that we've proven our hypothesis. Benzene does have a non-zero resonance stabilization energy. And since stability is key, some extra resonance energy should help, right?